Okay, so good evening. Welcome everyone to the IARCS verification seminar series. Sorry about the delay. Today we are happy to have Akshay from IIT Bombay. So Akshay completed his undergrad at Chennai Mathematical Institute, and then he did his master's both at IMSC and ENS Cachan, and he had a PhD degree joint between CMI and ENS Cachan. So he has worked on several things, motivated by automata theory, timed and hybrid systems, and now Boolean functional synthesis. Look forward to his talk. So over to you, Akshay.
Thanks a lot, Shri. Yeah, so everyone can hear me clearly, right?
Yes.
Yeah. Okay. Yeah. So yeah, thanks for this opportunity to speak at an IARCS seminar. I've been kind of wanting to give this talk to this community. I think some part of it maybe is a little bit familiar to some of them, some of the audience, but I'm hoping that there will be something at least new or fresh for everyone. All right. So today's talk, what I'll be talking about is on Boolean functional synthesis, and kind of my take on this is that here is a problem which requires a good theory and good practice, in the sense that you need to implement, you need to understand how things work, and then you need to go back to the drawing board and work out the theory and so on. And I hope to illustrate that by throughout this talk. Right. This work is actually a culmination of a long series of work starting from 2015 with mostly, I mean, all of it is done jointly with Supratik Chakraborty, my colleague at IIT Bombay, and Shetal Krishna have participated in various parts, and there is a whole series of generations of students who have graduated in this. So for those students in the audience, I would, kind of point these three generations of pairs of students from IIT Bombay who have graduated by doing their various projects on this topic. I would also like to thank a few of people, Priyanka Golia, Kuldeep Neal, and Subhajit Roy, for not only discussions, but also there's a joint tutorial that we gave at IJCAI 2022 very recently, and before that at AAAI 2022. And this talk draws a lot of inspiration and many of the slides from that other talk. Right. I think that's about all, and I will get started with the presentation. So, all right. So, I think so you can still see my slide, right, in full screen.
Yes. Yeah.
Okay, great. So what is synthesis? So when we start with synthesis, we're talking about a system which has some inputs and which has some outputs. And now this is what the system wants to be. Oh, right. This is not on full screen mode. I'm sorry about that. Yeah. Okay. So while that might be the system as an implementation, the specification is often easier to give in terms of, maybe by examples, by saying that for these pairs of x1, x2, these are the pairs of y. Or it might be a specification may be easier to give in natural language. So, for instance, you may be able to give it easier as saying output is the max of x1, x2, but if both are less than 10, then the output of y must be equal to 10. Or you could have that the specification can be as an input-output relation. And you can see that, as a relation, it's much easier to write logical specification as a relation rather than giving it as an implementation, as a function of which defines the outputs in terms of the input. For instance, here you have a formula which just says, some bunch of things which is the relation between x and y. And really, what we are interested in is if our specification is in the specific format. For this purposes of this talk and this piece of work, we are going to be looking at the format of input-output relations. Then can we have an automatic algorithm, a synthesis algorithm, which synthesizes some implementation of it? Is that clear? So that's kind of our goal in this talk, and we will try to kind of motivate this by various examples and show how this appears in practice, and talk about the theory and practice of this. Right. Okay, so let's understand this is a kind of a generic view of this. So remember that a specification is a formula which is in terms of the inputs and the outputs. So there are a bunch of n inputs and outputs, and what we want is to synthesize the system automatically to be designed, which will take as x1 to xn as inputs and give out y1 to y1 as outputs. Right? And the goal is really to automatically synthesize the specification. I mean, one may be interested, for instance, because later when we change the specification, maybe there is some small change in the specification. We don't want to actually sit and manually synthesize the implementation. We want to just feed it to this algorithm and get an implementation out of it. Right? This could be one motivation for this. Right. And I would like to point out also that whenever this is possible, I want it to be to happen. We'll go a little bit more into the detail of this.
Question.
Yeah.
There's a question on the chat. Akshay.
Already. Great. Okay. Specification is a formula. Yes. Currently, I'm in this talk, we are going to consider the specification in this generic view, which is as a formula of input outputs. Is that clear, Raghavan? Is that?
But you showed a table, so that's why I was a little confused.
Just to say that there are many different ways of specification possible. We are picking one of it.
Okay, great.
Yeah. All right. Let's see a more kind of concrete example, right? Let's say a specification as a bit vector formula. So, here is a bit vector formula, which is going to take something like y1. So this notation here is the bitwise multiplication. So it's saying that x is equal to y1 into y2, and it must be the case that y1 is not 1 and y2 is not 1 as n bit vectors, right? And I want to synthesize y1, y2 as a function of x. So does this sound familiar? So suppose we are able to do this problem. Does this sound familiar to people? It's not very difficult to see that what I'm asking for is to solve factorization, fixed bit width factorization, right? Where I'm asking for y1, y2 to be non-trivial factors of x, right? So if I could automatically synthesize a system doing this, capable of doing this, right, I would essentially break crypto system, fixed bit width, right? I'm not going to talk about arbitrary bit width in this talk, right? Does that make sense? For 2n bit width, so maybe of size 1024 bits, suppose I'm able to do this, synthesize such a circuit, I would crack RSA with 2056 bits or whatever. Right? Does that make sense? Is there a question? I think there is a question. Okay, there is no question. Okay. But if this is fine, so first question from me is this specification always satisfiable? What do you think? So yeah,
not always, right? If x is
not
prime,
always. Correct, right? Of course, x can be prime, in which case it's not satisfiable always, right? But my point, and this is really the crucial take-home point on the slide, one of the points, is that synthesis as a problem, this question still makes sense, even if the spec is not fully valid. That is, even if there are inputs for which there is no output possible, you may have the problem. What I want to solve is whenever there is an output possible, then give me the output. Does that make sense? Yeah. So really, we want to synthesize a system such that it satisfies the specification whenever that is possible, right? Okay. So actually, I wanted to go through the outline of the talk, but before that, I thought maybe let's maybe look at what this actually looks like in practice, right? I mean, I wanted to kind of do a small tool demo before we start out, even without having the talk. So, in some sense, are these factorization ideas up in the air, or do they really work? Okay. So to do that, what we have done is written a small script. I mean, the script is due to Priyanka Golia and Supratik Chakrabarti, and I will be using that for this demo, right? So let's look at, so what I'm going to do is to show you let's say, I don't know, let's look at factorization of 7 bits. Okay. So is this screen visible? Is this Emacs file visible to everyone?
Yes, visible.
Is this even better visible now? Yeah. Okay.
Yeah.
All right. So notice, so what I'm going to write this, so this is my input format. This is kind of basically saying that we are only talking about 7-bit arguments. You can pretty much ignore this. If you're not aware, I mean, with SMT format, you can just pretty much ignore this. I'm just saying here that this is a factorization and which is the input and so on, right? So these are kind of the syntax. And I want to point out here that I want, what are the constraints? I want that the input should not, I want to assert that it must not be equal to one of the inputs. And I want to, I want to say that it must not be equal to 1. So it should, so it takes as input the input 1, and I want to make sure that the output is not equal to the input, and I want to make sure that factor of input, which is the output, should not be equal to 1. Okay, so that's what this line says, not equal to 1, and this line says not equal to output, to the input itself, and this line says that there should be no reminder when I, so you should have no proper divisor. Okay, that's kind of what we are encoding over here, right? So the reminder when I divide by the output of the factorization should never be equal to 0. Yeah, does that make sense? Okay, so this is kind of the code. And let's see, so I'm going to run a demo on this, let's say, factorization 7, fine. Let's try this. Well, right? So we are running a demo with one of the tools which use this. So basically what this tool is doing is taking the bit vector, bit blasting it into the Boolean formula, and then calling our synthesizer. And then it also then converts it and calls a simulator. So now, shall we see whether it worked? So basically I'm asking for one input. So let's say, let's take an arbitrary input, let's say 45. And it seems to give a factor which is 3. Let's take 60. It gives a factor 4. Does somebody want to try something else? This online format is not the best suited for this talk. But nevertheless, I will persist. Let's try 17. Yeah, go ahead.
51.
51. 51 is 3, but 17 also it's giving 3. Right? So something is wrong here, right? Is it wrong? Well, not really, right? Remember, if it is prime, then the spec is not satisfied, then I don't care what output is given. So I don't care what it is, and I can easily check that indeed 3 is not a divisor by multiplying it and checking whether it multiplies. Is it a factor of 71, right? So indeed, if you notice any prime number, I mean any composite number is fine, but if I take any prime number, I don't know.
So there's a proposal 29.
Oh, 29, thank you. Yeah, so 29 also it gives a 3. It seems to always give 3, right? But does it? We can try that out also, right? So 84, it gives 2 suddenly. 87, it gives 3 suddenly. So basically what I'm trying to say is that this seems to work, right? But what does this mean? I mean, maybe I just in the backend wrote an algorithm for it. So does somebody want to try one more output before, one more input before I show you the circuit for this? Bhavana, do you want to suggest one more input? Otherwise, we can go ahead.
11.
Excellent. Oh, great. 11 also gives wrong output, obviously, because it's a prime, but it gives a different wrong output. right? Okay, great. All right. So now, to show that I haven't cheated, let me show you the circuit which this has produced. So remember, this is 7-bit bit vectors, right? So it's, you will see the size of the circuit should be interesting. Oh, there is the circuit. Okay. And I don't know what you can see from this. Perhaps the only thing one can really observe is that the number of outputs is 7, right? And I guess number of inputs was also 7. So you took 7-bit numbers as input, and you give out 7-bit numbers as output. That's pretty much all. But otherwise, the circuit is indeed too difficult to analyze by hand, right? So this is indeed the case. Maybe let me take another minute and show you one more example, and then we will go into the rest of the talk, right? So I had prepared another short. Let me see if I can show you that. Okay, so you see here. So this is something which is also interesting. This is saying that it asserts that the output of the function, it takes 2 bits as input and gives 1 bit as the output. It says that the output of the function should be greater than equal to the first input. The output of the function should be greater than equal to the second input, and the output of the function should be either equal to the first input or the second input. So what is this synthesis? What is the specification? What would it synthesize? What do you think?
Max.
Max, right? So indeed, if you see this, sorry about that. Now, and indeed, you can see that if I do 4,5, it gives 5, and if I do 1,9, it gives an error. Why? Because it says and exits by saying that the value of the input is not a 3-bit number, right? The reason I showed you this example is not so much for the simulator, which is of course trivial, but I wanted to show you the circuit, which is a little bit more meaningful, and then we will go into the talk, rest of the talk, right? So indeed, in this case, let's kind of show the circuit which was generated here. Yeah. So in this circuit, you can see that indeed it took 2 bits, 6 bits here, 3 bits input, 3 bit another input, and it produced the output. And you can see that the max bit here, for instance, right? Somehow, if you see the V8, it's basically, this is what is called an AND inverter circuit. So these are all, these dotted things are negations. So this is negation to here and negation to there. So otherwise, this is pretty much what you expect. And you can kind of infer somewhere that it is trying to take the maximum bit and taking its value, right? This is just kind of some level of intuition on this, right? So I think this, I'll stop kind of showing off the circuits here, and we'll go to the talk. And then at the end of the talk, if there is enough time, we can come back and change this code. I mean, the whole point of this demo was to be able to change this code. For instance, if I change this to greater than, and if I change this to greater than, then what should it give, right? So things like this. So we can try this out at the end of the talk, but you will have to stick along till the end of the talk for that. All right. So I will now get back to my talk. So we will try this at some point. You will see that there are some interesting things which happen when you do that as well. So if you see this, it gives a completely different circuit compared to the earlier one. And what changed here, we can look at that later at the end. Yeah. Okay, great. So that's kind of my first part, and that brings me back to the talk. Oh, I just saw the 47 from Bhavna. Bhavna will try that at the end of the talk if there's time. Yeah. Okay. So is that fine? Are you all with me here? Are we convinced that this problem can produce beautiful circuits? Right. Okay. So now let's start with the outline of the talk. So basically, I want to go through, this is the kind of broad outline. I'd like to go through the formal problem statement. I hope we already have an idea, but I want to fix the notation. Then we'll look at some old history and recent applications. Then we'll look at some theoretical results. And then depending on how much time is left, we will go into more in-depth things. So most of the talk will be at a very high level, but there will be some 2-3 parts where I will try to go into depth of some amount of details in this talk. Right? And then we'll look at conclusion and what problems are open and so on. Okay, so let's start with the problem statement. Right? So just to kind of reiterate and make sure we are all on the same page, what we are given as input is a Boolean relation with over inputs and outputs. So there are a bunch of input variables, x1 to xn, and output variables y1 to ym. And what we want to do is to synthesize Boolean functions, one for each output variable, such that, right? So this is just a notational way of saying what we have been saying all the way till now, such that for any input, if there exists a value of the output which makes the specification true, then substituting these functions for the outputs must make the specification. Does that make sense? Do we agree that this is what we have been talking about till now? Yeah. Such functions, f1 to fm, are also called Skolem functions for these variables in the given formula. Okay. So what do we want? We want to synthesize functions such that if there is a way, if there exists output valuations which make the formula evaluate to 1, then substituting the variables, the output variables by these functions must also make the formula evaluate to 1. Okay. So such functions are called Skolem functions for these variables, right? And why are they called Skolem functions? It's a bizarre choice of word. Actually not. It's in fact steeped in logical history. And in fact, if you have done a first course on first order logic, you would have seen this whole idea of Skolemization, which is really talking about getting rid of existential quantifiers. And this is really work going back to Thorald Skolem in 1920s and Jacques Herbin in 1930s. And really the idea there was for first order logic to be able to do this. But of course, the focus there was on existence of such functions, not really on computability of these functions. Does that make sense? But actually, if you think about the history, it turns out that you can trace the history back even further. You can look at these unifiers looked at by Boole and Lowenheim in all the way back in 1850s and 1900. And so Skolem functions can be thought of as there is a kind of a link between this existence and construction of Boolean unifiers and Skolem functions, which are one type of Boolean unifiers, right? So this is just to say that there is like a really old, kind of pedigree to this problem, right? And we are, of course, interested in the Boolean variant of this problem. So before I go further, BFNS is just a synthesis. Let me just kind of, not exhaustive, but set of applications of this. So let's start with one, which is maybe something which is kind of current interest, which is on program synthesis, right? So just as you have Boolean function synthesis, it turns out it can be used for synthesizing programs. So for instance, if you have this program here, and if you are asked to synthesize a program for a function G satisfying these constraints, then what you can do is to actually introduce a new variable and synthesize, consider this formula and synthesize a Skolem function for this variable in terms of the input, and that will turn out to be a program. And in fact, this is exactly what is done in this work by Priyanka Golia, Kuldeep Meel, and Shubhajit in 2021, right? And in HKI 2021. And this really shows kind of the application or the link between Skolem function synthesis and program synthesis. There are also strong links between and a little bit unsurprising links between Boolean functional synthesis and QBF in general and planning, where strategies in games, synthesizing strategies can be reduced to synthesizing Boolean functions. So there is a link in this, and again, I won't go into this in detail, but I can talk to you offline, or we can talk about this in detail later.
Akshay, can you just show that program synthesis application again? I missed that. It's a little small, the font.
Oh, I see. Yeah, the reason I deliberately kept it small was that I didn't want people to ask questions on that. But yeah, please ask any question that you wish.
Yeah, sorry. So what is here you have to synthesize a program satisfying G, is it? Sorry,
yeah. So you want a program for G. This is your specification. Okay. This is the max. I mean, this is just another way of writing the max, right? So basically, if your spec had been that in this way, and you want to synthesize a program, then you can write that as introduce a new variable and write this as a formula, and then ask to synthesize y1 in terms of x1 and x2. And the circuit that you get will be a program.
Okay, so phi is that formula above, the conjunction of those.
Yes, so this is correct. Thanks. I wanted to write it there, but I thought it would clutter it too much.
No, the one above, I mean, on the right.
Yeah.
Right pane, right?
Yeah, this one also. Yeah. So in this one, yeah. Sorry, this one is phi. Yeah.
Okay.
This whole thing.
Okay, fine.
Yeah. Okay. Great. So I mean, yeah. Go ahead.
One question. So about the definition. So
yeah.
I mean, from the previous whatever the examples, it looked like we want a function, a function which can return all the outputs simultaneously. So here there are M functions which do not communicate with each other. Isn't this a tougher problem?
Actually, these functions do communicate in the sense that the way they will be constructed will be one using the other. So very often, and in fact, in this doc itself, you will see that I will construct one using the other. And then finally, of course, when you substitute back, you will get all of them separate. All in terms of only that.
Yes. Okay, fine. Okay.
Yeah.
Thanks.
So Akshay, that was not Boolean function, right? I mean, this example that you gave, the program synthesis.
So that's true, but usually the way that, at least in this paper, they handle it is to bit blast it into Boolean.
Okay.
Yeah, that's often what many of the techniques do finally. I mean, currently that we know of, we still are in the nascency of trying to do. There are techniques which directly tackle arbitrary. In fact, Kunchak et al. Is a paper which does complete functional synthesis without bit blasting, but I won't go into that in this talk, except in future work. Yeah. Is that fine? Shall I go ahead?
Yes, thanks. Yeah.
Okay, so it's not surprising that quantifier elimination is indeed one of the applications, but quantifier elimination itself has many applications in image computation, in decomposition of relations, and so on. So again, that's a very kind of thing. There's another kind of set of applications into circuit repair, where we are talking about synthesizing some pieces of the circuit where there is some holes, and you want to synthesize some circuit which satisfies the entire specification. And finally, there is a reactive synthesis where you can see that the ground problem can be modeled as this. And in fact, there are tools which have also tried this approach. Though I must say that the current scalable tools which do reactive synthesis do not use this approach. It's a question of time, I think. All right. So this is just to say that there are a lot of applications, and which is kind of why we are interested indeed in this problem. And that brings me to kind of the theoretical hardness and practical algorithms. So at the level of theoretical hardness, you would not at all be surprised that, first of all, when I say hardness, I have to first tell you how to represent these. I will be representing them as Boolean circuits in negational normal form. Negation normal form is where I'm going to use. Later, when we need it, I will define what it is. Okay. None of us, I think, will be surprised if I tell you that Boolean functional synthesis is NP hard. Okay. I won't even prove it. but you can see that there is a one-line proof for it. Take only the outputs, don't take any inputs, and then it becomes an instance of SAT. Okay. But what is more interesting is that it turns out that unless the polynomial hierarchy collapses, there exists a specification for which the Skolem function sizes are super polynomial in the size of the input. Okay. So again, if you don't know what the polynomial hierarchy is, don't bother. Just say there are these conjectures that complexity theorists have made, which are very, very unlikely to collapse. And according to that, you cannot have polynomial Skolem functions always. In fact, you can prove even stronger things by even weaker or even stronger hypotheses. There is this hypothesis called the variant of the so-called exponential time hypothesis. And unless that fails, you can actually show that Skolem function sizes in the worst case may be exponential in the size of the input. Okay, so it's not very important what this exact class is. I think what is important is the bottom line, which is that efficient algorithms, extremely unlikely, right? It depends on your belief on complexity theorists, but as long as you trust in their conjectures, it's unlikely to happen, right? So despite that, so I've just said that these problems are super interesting, but they are super hard. So then what do you do? Unsurprisingly, because of the hardness, maybe not despite the hardness, but because of the hardness, there have been a huge set of techniques which have been developed. And, given the Marvel craze right now, one can break it into 3 phases. Right, I won't again go into all this and bore you, but it turns out that there is a whole bunch of techniques which were used from 2005 to 2013, and there is a new set of techniques which came about in phase 2 of Boolean functional synthesis, which was in more recent times. And maybe in the last 4 years or something like that, or maybe even less, last 3 years, let's say, we are really in phase 3, where we are looking at kind of 2 particular techniques. And the rest of the talk, I'm going to actually focus on the techniques in phase 3, right? But that is not to say that the early techniques were not relevant, or they are not. There are interesting ideas. For instance, that incremental determination really exploits SAT solvers. There are ideas from self-substitution which are used inside some of the state-of-the-art tools and so on. But I just wanted to kind of point out that these 2 are the kind of state-of-the-art techniques, and we will, in the rest of this talk, go through both of this and maybe try to understand a little bit details of this. The first idea will be on what is called the counterexample guided Skolem function generation. This is a classical Segara type technique, but with a few new tidbits. And the second is motivated more from AI, which is this idea of knowledge compilation and representation. And this again will be kind of motivated from work on knowledge representations and AI, right? Okay, so this is actually a very good time to stop and take stock because I'm going to now go to the deeper part of the talk, which is about 20 minutes from now. I started about 10 minutes late, is that right? So do I have 10 minutes?
Yes.
Okay.
So we can aim for 8:10.
Excellent. Yeah. All right. So in that case, this is kind of a good breaking point. Is there any other doubts? Is the problem clear? And kind of broadly, is it clear what our goal is for the next 20 minutes?
Akshay, it's just maybe is there some trivial upper bound? You gave only
exponential time.
Time.
That's right.
Okay.
You're right. Yeah. Because these are finite domain stupid things, right? We can always enumerate everything and do it in exponential time.
Oh,
yeah, I should have mentioned that. Yeah. Somebody asked this question already, and I thought I should write it down. I forgot to. Yeah.
Thanks.
Yeah. So the Boolean case is exponential. Okay. Thanks for that question. Okay. So you can, the fact that this is NP-hard means that I'm going to throw SAT solvers whenever I can throw them. Okay. So there's nothing going to stopping me from throwing SAT solvers and trying to solve the problem, which is what we are going to do several times in what is coming. Okay. All right. Anything else?
Akshay, you should just get on with the talk because there's not much time.
Yeah. All right. Okay. So let's go on. So let me maybe go into a little bit more detail. So maybe I'm going to have about 5 important ideas that I want to convey, which are more technical ideas. And these 5 ideas together will kind of give you the basis of both these approaches that we talked about last. All right. So let's look at these basic ideas, which are also kind of the core ideas. The first idea is that checking column functions is easy. What do I mean by that? If I give you a function and if I ask you, is it a correct column function? I claim that that is easy. But what does it mean to be a correct column function? Again, remember that my column functions, I mean, there are M of them, right? Srivatsan pointed this out already. So when I say F, I really am doing some abuse of notation. That's really a vector of functions that I'm talking about, right? So normally I want to check this query, right? And this looks like a 2QBF query, right? So there is a for all there exists alternation. The question is, can you stick to SAT solvers? For me, again, easy means, can I solve it using SAT solvers, right? So this is a 2QBF query. Can I solve it using SAT solvers? And it turns out that we can. And this is kind of the first maybe core idea which makes things work. Consider the following formula. Okay, here is the formula. The formula just says that take a new set of variables, y prime, fresh variables, one for each output variable. Take phi, the original formula, conjunct it with a copy of the phi negated, but with new variables instead of the old output variables, and set each of the new variables to be what is output by your candidate functions, your guest functions still. Okay. So the better way to understand this is to see what it really does, right? Let's take a satisfying assignment of this formula. What does a satisfying assignment of this formula do? A satisfying assignment of this formula means that there is a way for the formula to evaluate to true, but if I go by what my current guess of column functions is, my current candidate's column functions tell me about the outputs, then the formula evaluates to false. That means some function must have been wrong. I don't know which one, but something must have been wrong, right? That's exactly what we say here. So the phi with xy is true. This is set according to this column function, but with this set thing, then there is a error. The formula evaluates to false, right? So this satisfying assignment, in fact, is a counterexample to the fact that these F1 to Fm are all correct column functions, right? What this also means is that if this formula is unsatisfiable, then all these must be correct column functions, right? So we did close to this, right? So basically, instead of having a SAT query, we have reduced it to an unsat query. But for a SAT solver, it really doesn't matter, and hence we have accomplished our first goal, right?
So Akshay, I have a question, if I may ask.
Sure.
Would this tend to reject F if the given relation was unsatisfiable? That is, if there is no
Correct.
way to synthesize a function.
So if there's no way to synthesize the function, I don't care, right? That was very important, because in this case, if there's no way to synthesize the function, this will also give you 0. So what the error formula says is ridiculous at that time. I mean, it doesn't make, there is no...
The error
no
formula
meaning.
would give you satisfiable, right, in that case? Because the F would be wrong, and so it would say satisfiable.
So whatever it says, we don't care. That's what I mean. Basically, what it says may not be correct. It may say satisfiable even if it's unsatisfiable.
In that
Correct.
case, how to know that that original thing is not synthesizable?
So that's not currently what we are assuming that we are not trying to check whether it's synthesizable or not in this question, right? Currently, we are trying to ask if I don't care about it, like in the factorization case, it's easy to check whether it's synthesizable. I mean, whether your current output is correct or not, right?
Okay.
Because you can just substitute back in and multiply and you'll get the answer, right? So here we are worried about whenever there is a right answer, you must give the right answer. Whenever there is no right answer, you do whatever you want, we don't care. So the way to check it will be, you take it and substitute back and check whether then it satisfies the relation or not. So I will take my answer, whatever the current candidate functions are, and I put them back in and then check whether it evaluates to 1. Yeah. Is that okay? Okay. So now the second idea, maybe the second core idea, is that the one output
Sorry,
case.
so when you say first core idea, what does idea do? Is it for
just
synthesizing
saying
the
that,
F, or is it only for checking?
just for checking. Just for checking. I've not solved anything. I've just said checking is easy.
Okay.
That's all. I mean, simple ideas. So the second idea is even more simple. It says that if you have only one output, then column function synthesis is easy. The full problem, right, is easy if you have only one output. Okay. So let's go through this a little bit. I claim that if there is only one output, then phi with x and the constant function 1 is actually a correct column function. And hence it's very easy because you just need to substitute y by 1 and it turns out magically that it is a correct column function. So this seems a little bit like magic, right? So maybe I will take 1 minute and give a proof for this. Okay, the proof does look like magic, but you will see that it's actually very simple, though the intuition of it is quite, I mean, once you get the proof, of course, it's very simple, right? So basically, what does it mean for this to be a correct column function? It means that if there is a way for any x, if there is a way to evaluate phi x y, if there exists a y1 such that phi x y1 is 1, then when I substitute y1 by phi of x1, it must evaluate to 1. So first thing I observe is that this is the same as saying in the Boolean case, exists y1 is nothing but this. Do we agree? So I need to show that this and this are the same. And that doesn't seem completely trivial, but let's actually do the proof and you will see that it actually holds. So what is this? I mean, it looks a little bit weird because of the self-substitution sitting there, but you will see that actually it does work out, right? So if consider this formula, phi x1 disjuncted with phi with x0, then if I substitute, if I take, suppose the left-hand side evaluated to 1, right? Then it must be because of one of these guys. So suppose it evaluated to 1 because phi x1 was 1, then of course the right-hand side also evaluates to 1. Suppose it evaluates to 1, but this part was 0, then this must have been 1. But in that case, this would have been 0. So you would have got phi of x0. So right-hand side would have evaluated to 1. Similarly, you can argue that if this evaluates to 0, then right-hand side also evaluates to 0. So actually, it's just like a little bit of manipulation, and it shows you that phi of x1 is a correct column function. And in fact, it turns out that there are many correct column functions. The negation of phi of x with 0 constant is also a correct column function. And in fact, any interpolant, that is anything which is implied by one and implies the other, is also a correct column function. And this is all something which you can prove just like this, using simple ideas. Okay. Is that fine? So is that second takeaway point clear, that the one output case is rather easy? Now, the third idea. Okay, the third idea is a little bit more tricky, but I'm not going to go to the proof of this. I'm just going to say that to be able to compute column functions, you need to be able to do existential quantification. That is, for any I, you need to be able to do, what can I say? This is, if you can do this, then you can easily compute column functions. That's all I want to say. It's only one way I want to claim, right? I just need to compute exists y1 to yi, phi of x with y1 to y. So I want the quantification over. So this is a formula which depends only on yi plus 1 to ym and the inputs, right? And why is that? So just a quick intuition. Again, I won't go into the details here. Basically, what you can do is, if you have a specification with multiple outputs, you can transform it back into a one output case by using the fact that you can compute existential quantification easily. How do we do that? Basically, you take this, kind of quantify out one thing, then what you have is a resulting formula which depends only on one output. Then you synthesize this column function, then you substitute back it, and then you will get basically this column function automatically. Right? So it's basically some idea of this substitution which allows us to do this. The only tricky part here is coming up with this existential quantification, partial existential quantifications effective. Okay. So that's kind of going to be what we focus on in pretty much the rest of the talk. So this existential quantification turns out to be a very important concept. And for that, I want to point out, I want to recall that we started by looking at negation normal forms, right? So we had negation normal form of a circuit. What was a negation normal form? It just basically means that negation is only at the leaves and the circuit inside has only AND and OR gates. So negation is all at the leaves and the circuit has AND and OR gates. So substitute y1 to be equal to 1, then in the negation normal form, this is the same as setting y1 to be 1 and negation y1 to be 0. Because if I put y1 to 1, the negation y1 must be get to 0. Similarly, I can consider y1 to be set to 0. That is nothing but putting y1 to 0 and negation y1 to 1. Right? Now, what is existential quantification? Existential quantification, remember, is nothing but the disjunction of both of these circuits. Correct? Again, not surprising at all, right? I mean, it is just saying either one must be true or y1 must be 1 or y1 must be 0. And this is exactly the circuit we drew. So this is the disjunction of both of those is existential. But this is what I wanted to do. I wanted existential quantification and it seems I already have it. So what's the problem? Well, there is a doubling of size, right? So each variable I'm doubling and I want to totally avoid that. Otherwise, I'm going to have an exponential problem, right? So how do we avoid that? So one way to avoid that is using this.
Akshay,
yeah.
Akshay, if it's okay, I mean, I do not understand the previous slide. So we are supposed to
I can
output
go through
2
this.
bits.
Yeah, sure.
We are supposed to output 2 bits y1 and y0. Is it correct?
So yeah, so these are the, I'm just taking the specification. Now I'm just manipulating the specification, nothing to do with the input output anymore. I mean, input output are of course there. Y1s are output, X's are input. But I'm just talking about the specification and I'm getting another specification which is exactly equivalent to that. I'm just manipulating the specification. This is the specification.
So in this case, how many outputs are there? 2 or like 2 outputs? Is it?
Y1 to yn, n outputs are there. This is a vector. So basically X is just notation for X1 to Xm and Y is notation for Y1 to Yn. N and M I may have confused, but yeah. Is that fine?
So here the fee is a possibly quantified formula. Unlike the earlier fees, it was only a this Y1 fee.
Right. So this is the formula which is quantified, and I want to say, so where do you want to? Which one are you talking about? Deepak, what I'm trying to say is that if I take this formula, just this guy, this is phi with y1 set to 1 and disjuncted with y1 set to 0. So that is exactly the same as doing an existential quantification of y1.
Yeah.
That is only that y has only 1 bit, right?
In this case, y has only 1 bit. I mean, yeah.
Raghavan,
So
I think the confusion is that in the fee that he's writing actually has there exists y2, there exists y3, up to there exists yn, and then there's
so you're asking what happened?
Yeah, I mean, I was
if you
thinking
don't
that
like
there's
it,
only
you
one
can...
output anyway. It's easy. So why are we struggling with?
Correct.
Only one output.
Okay. Okay. So what I mean is that indeed in this case.
Yeah, go ahead. Sorry.
Yeah. No, in this case, the fee does have the other outputs sitting inside it. I think the notation is not written very well, but the idea is that this is a multi-output function. So here you have y1 to yn, all of them as part of y, and we want to eventually quantify out not just y1 but all of them. I'm just telling you how to do this. So remember, I'm now gone from, I just want to come up with a normal, I want to come up with an idea about how to take care of this existential quantification. So we will, maybe you can stay with me for one more slide and I think you will get the idea.
So Akshay, how does, maybe I missed that also, how does, if you can do existential quantification, how does that help you solve the problem?
So the existential quantification, once you can do, you can basically, when you existentially quantify out, then the remaining part you can make it depend only on one output. So you can reduce it to multiple instances of the one output synthesis. If you can do existential, this is basically, this is for the two output case I've given this, but in general, you will have multiple, iterations of this.
Okay, so maybe I missed that, but I thought in your problem, the phi that you have, the phi of xy is quantifier free.
Yeah, right? So the phi is quantifier free, but it depends on all the inputs and outputs, right?
Right. No, but I mean, so what do you mean your new spec is?
So which is why here,
your new spec is
oh, I see.
That form.
That is the confusion. So, correct. No, right? It is of that form. It's just that phi now depends only on x and y2, x1 to xn and y2. It doesn't depend on the other guys. Oh, I see. Oh, sorry. Yeah, there is a type. Okay. So so it has y3 to yn also, if you wish. Yeah. In this case, this is a special example where there are only two outputs. I think that's the confusion here. This I tried to give using an example. So assume that there are only two outputs, and I'm telling you here, if there are only two outputs, then this guy depends only on the inputs and the second output. Do you agree? So is that fine? So this formula,
only on y2, yeah, x and y2.
Only on y2. So it has one output.
Right. No,
by definition.
I'm saying that this is, I mean, this is no more a quantifier free formula, right? The phi in your original problem.
Sure.
Wasn't the phi a quantifier free formula?
That was just the representation was quantifier free, but basically I want some formula which is equivalent to this, but whether it's quantifier free or not, I don't really care at this moment, right? I just want them to be equivalent. Okay. So I want a representation for this. In fact, you will see just one slide later that I won't do actually exists y1. I will do something else.
Okay, so you will eliminate y1 from that phi, is it? Is that the...
Correct. That's the goal. That's the goal.
Okay.
Does that make sense? Raghavan, does that make sense? Let's go maybe two more slides and then we'll get this idea.
Yeah.
Okay. So the point I'm trying to make is that now actually what we will do, therefore, is to consider the so-called positive form of the formula, which is nothing but you replace all the negation of y1s by y1 bar, and all basically for all the outputs, only for the outputs. So in this case, let's say for the first output, I replace the negation of y1 by y1 bar. I keep everything else the same, and I consider that to be phi hat. Does that make sense? So in this formula, I have introduced a new variable y1 bar, and I have replaced all occurrences of negation y1 by this y1 bar. Now my point is that in this circuit, in this phi, which is indeed a quantifier free circuit, right? This NNF circuit here is quantifier free circuit. It's just a circuit sitting there, right? In this circuit, y1 and y1 bar, right? There are no negation gates inside. So y1, there is no negation y1 anywhere in this circuit. So it's monotone, right? And therefore it's monotone, and similarly there is no negation y1 bar also. So y1 and in y1 and y1 bar it is monotone. What does it mean to be monotone? It means that if with y1 bar I make something 0, then with y1 bar when I set it to 1 also it cannot change value, right? In other words, if I take this formula here, this formula is exactly the formula which looks at y1 bar and puts that y1 bar, which is back to negation y1, so putting it to 0. If suppose this formula evaluated to 1, then this formula that I have here, this circuit that I have here, must also evaluate to 1. Why? Because it is monotone in y1, and therefore by putting monotone this side in y1 bar, therefore if with y1 bar equal to 0 I have the formula evaluating to 1, then with y1 bar equal to 1 also the formula must evaluate to 1. Okay, so the formula that I have here implies this formula, which is this circuit. And similarly, notice your output variables, right?
Sorry,
Hi,
this,
looks like I conked out, huh?
yeah.
Okay. Sorry about that. Where did I conk out?
So the bottom left, if it is 1, then the top one is 1.
Yeah, if this evaluates to 1, then the top one must evaluate to 1. Similarly, if this evaluates to 1, this must evaluate to 1. Therefore, the disjunction evaluates to 1, which means that I only need to look at this formula, and this will be always a over approximation of this formula. That is, the existential quantification always implies this formula. And notice that in this formula, I don't have existential quantification. It is of my original form. It's quantifier free, except it has one more variable there. Deepak, is that clear now?
Yeah, not very clear, Akshay, but I think you go ahead. Yeah, I'll ask you again later.
Okay, fine. So essentially what I'm trying to say is that this was the construct that we had in between to say that the existential quantification of y1 with phi xy does in fact imply this formula where you take the positive form, which is basically you replace all the negations of the outputs by new variables, and then if you set both of these to 1, this entire formula will be that formula that you obtain here will be an over approximation of the existential quantification. Okay, this is kind of the most complicated idea. So if you I mean, in some sense, after this is the direct algorithm. So let's kind of go to the algorithm, and if there are doubts, I can clarify that later. So remember this idea, and we'll come back to that anyway later. Okay. So if we connect the pieces, what have we done? We saw that checking whether a given function is column function is easy. We saw that single output case, there is a easy column function. We saw that existential quantification is key, and we saw that over approximation is easy, right? I will also kind of throw this that we should always do some pre-processing. If you know some variables are easy to handle, you should always do them before you do any algorithm. Right? For instance, if you know that the phi with y set to 0 always implies phi with y set to 1, then 1 is always a column function. You always set y to be 1 and it will always be correct. Right? Why should you even synthesize column function? Just do the unit check. Similarly, if you know that some variables are uniquely defined by some other variables, then you don't need to synthesize column functions for them. Just synthesize for the others and then plug them in. So these are some basic ideas, and using these ideas, if you put them together, we get actually the first kind of set of algorithms that we had, which is what we call the guess, check, repair set, right? Where we do pre-processing, as I just explained, where the check is like which we discussed. The function-based approximation we discussed, the machine-based approximation we didn't discuss in this talk, but it turns out that that's what one of the approaches does. And the repair we didn't have time to discuss, but essentially, if you take that counter example that we had, one satisfying assignment, you use that satisfying assignment to repair the formula. So in fact, it turns out that the successful approaches which exist do a lot more. So for instance, there is this tool called blazingly fast column synthesis. What it does is approximations, it does a little bit more, and the repair, it does some more generalization. Then there is a state-of-the-art tool called Manthan, which second version is out already, and maybe the third version is in building, where the pre-processing also has extra. The main kind of innovation is in the guess part. They use heuristic sampling and decision tree learning to come up with better guesses. And then the check is exactly the same as we discussed. But the repair is by using a little bit more than what, by just instead of having one counterexample, by looking at unsat cores and generalizing counterexamples. But essentially, this gives you the core idea behind two of these state-of-the-art tools that we have. Okay, so if I have 5 more minutes, I wanted to look at the ideas on knowledge representation. But if there isn't time, I can go to the conclusion directly as well.
Yes, I think, Akshay, we are running out of time. We should,
Okay.
maybe it will be good to have some time for a couple of questions at least. Yeah.
Okay, so then in that case, what I can do, maybe, yeah, let me just quickly, let me see if I can just get to the conclusion. Are you able to see the summary?
Yes. Yes. Yeah.
Yeah. Okay. So yeah. So basically, I think maybe we had some interruption and late start and so on. But essentially, I hope what we have convinced is that functional synthesis is a kind of fundamental problem with many applications in many domains. And there is a long history of work. And today we were able to just look at one idea, but it turns out there are very nice other ideas as well. And I didn't have time to go into some of them, but hopefully we can have another talk on that at some other point in the future, right? How does all this perform? Okay, so it turns out that if you look at about 609 benchmarks, which are coming from QBFeval and so on, in 2018, about 247 of them could be solved. But if you see in 2021, we can solve about 509 of these benchmarks using all these tools which exist. Right? These are benchmarks which are coming from, including factorization and so on, but using QBFeval computation benchmarks on 2QBF thread and so on. And you can see that we have a lot of, we have achieved a lot of progress in the last even 5 years. What this means, in my opinion, is just that more richer benchmarks are needed, right? So that brings me to kind of what future directions are there. I wanted to kind of maybe give 2 minutes of that. So let's maybe do 2 minutes on this and then end the talk. So the first point I want to point out is that in all these approaches that we mentioned, we are coming up with some Skolem function, but we are not looking at what is the size of the Skolem function, or are we optimizing on the Skolem function, or is it more readable, or is it using only some type of gates and so on. So to come up with such things is, I think, something which is very exciting future direction. Similarly, we are coming up with one Skolem function. Can we come up with many of them? Can we come up with all of them? Can we say, can you enumerate all Skolem functions? Can you sample them? Can you count and say how many Skolem functions are there? This would be a very interesting line of research. I think both of these are currently maybe a couple of thrust areas. The third kind of thrust area is on going beyond propositional logic. For Skolem functions are defined even over first order logic, as we saw in the beginning. But what should be the notion of computability, right? And a first proposal for this we have made in MFCS 2022, where we have said that we should be really talking about Turing machines as always to define computability. And this is slightly kind of not obvious because in the literature and the community, usually Skolem terms were looked at as one notion of effective computability. And using this notion of Turing machines as computability, we can actually go beyond propositional logic to first order logic in theory. So it turns out that we can show some nice theoretical results here, but no practical results are there, and we don't have any tools. And this would be a very exciting area of research. In fact, that I wanted to point out that, in fact, SAT, after all, from SAT, Boolean SAT, we have gone off to SMT over all kind of theories, and many of these are now scalable, LRA and so on. And can we lift synthesis techniques? So this brings back to one question which was asked earlier. Instead of bit blasting, can we directly do over bit vectors? Can we use some of these techniques that we have developed in the Boolean case over bit vectors? We don't, right? And so that's kind of where I want to stop this talk. Yeah, I'm open to questions, and if you want, we can do more tools, more examples. That's
Yeah. Thanks a lot, Akshay. The main principles behind this entire field of research was very enjoyable. So, are there questions?
because people are tired after 8:15 talk.
Yeah, sure. Maybe I'll just ask one question. So you said that it's not working well for reactive synthesis, as in it's not very scalable. So is there some reason why?
So yeah, that's a good question. So currently there are, so we don't know actually, Shri. So the last work that I know which applied this for reactive synthesis directly was this tool by Ochan and others called Absinthe, which was already 2015. So if you think about my phase 1, 2, 3, it was in phase 2. So the phase 3 techniques have not been applied and tested out. So we don't know whether it really works or not, but I feel more, basically the point is reactive synthesis has two parts of work, right? So you need to compute the winning region, and then you need to synthesize the strategy, right? So you need, there are other things which need to come together as well for this reactive synthesis. And it's not yet clear to me what should be the right, right approach. But it's worth investigating again. Yeah, I think. And I think I know at least 1 or 2 groups which have already started on this using Boolean column synthesis for reactive synthesis.
The game strategies, is it related to reactive synthesis?
Yes, yes, yeah.
So is the strategy itself fully as a Boolean expression, or do they use the Boolean variables to switch between the strategies?
So we have, well, so I don't know. So it depends, right? Basically, when people talk about reactive synthesis, they want, in the community, they want to synthesize transducers and so on, like closed form solutions. So whereas here, when you're giving an algorithm or a Turing machine essentially, or a circuit, so the representation of this itself becomes different. So I don't know. Possibly it will be possible. I mean, possibly it will be, eventually when the technique matures enough, we should be able to synthesize not the entire strategy itself, but currently we can synthesize. I don't know currently what we can synthesize, to be very honest. I think this is kind of open. What's the right way to do this in the reactive case? I just want to say that it is very highly motivated and we should all work on this.
Okay.
So Akshay, in the applications in this, so you mentioned that one of the future directions was to look at trying to synthesize Boolean functions with some constraints, maybe on the kind of gates or
yes,
maybe.
Yeah.
So what would be, so I mean, where are those practically motivated? Like, is it like in the circuit repair, or and what would be reasonable repair, constraints for these?
Right, that's actually, yeah, so that would be, I think, a very nice question, because for instance, smaller circuit is of course a natural thing to ask for, right? But smallness is not the only thing, right? As we saw, we may have good forms for the circuit which may not be small, but they may be easy to synthesize. So we should be doing easy to synthesize, easy to work with, easy in some other way. If you're looking at some applications, maybe readability of the circuit is what is needed. Maybe planarity is what is needed. I don't know. So it's, I think it will be dependent on the particular application. So if you're, for instance, looking at applications coming from, I don't know, factorization, you may be interested in circuits which are more smaller, because circuits are already, the specification is very big. But in fact, there was one, when we gave this talk last time, somebody was interested in coming up with a circuit which is for cryptographic reasons, which is as complicated as possible. In other words, they wanted to come up with a circuit which can be obfuscated, right? So you want a Skolem function which is not human readable or not analyzable. So maybe for some application like obfuscation, the right thing to ask is as complicated a function as you can get, a circuit as you can get. So I think it's really user dependent.
Also, in small circuits may have output instabilities.
Yeah, that's true also. Yeah.
Sorry, what does that mean?
So it may be, yeah, sorry, go ahead. Who was
Alvin.
If it depends on two input variables, and the output may settle down to a different value depending on which one flips first. Like, or there, it might not directly jump into one value, but it might take two different sequences values to settle into one final output.
Yeah, that is relevant here.
Yeah, so I think really this notion has not been defined, to my knowledge, by anybody, that what should be the right quality. And I think depending on what, like for instance, if you look at program synthesis, one of the criticisms of the circuit generated is that they are not readable, because you want programs to be readable, right? You want them to be easily understandable. You want it to be decision lists. You want it to be things which you can not only implement but understand. So whereas in circuit repair, maybe you don't care, and maybe in other things you don't care. I don't know. So I think it really depends on the particular domain of application.
Okay, so I think it's a good time to stop the recording or the main part of the talk. Yeah. So thanks a lot, Akshay, and thanks a lot everyone for the questions. Yeah, let's thank.
Thanks, Akshay.
Thanks.